transmitted radar pulse. It fundamentally has an envelope like this, right? That would be a voltage. Then it would be multiplied by a very high frequency signal. So you basically have something like this, and you're familiar with this from your communications courses, where you're gonna have a whole lot of pulses there, right? That's still a voltage. That's fed to an antenna, if you follow me on this. Now, what is transmitted from the antenna is power. So if you look at the actual power waveform for this, it would still have an envelope like this. Then it would be proportional to V squared times some factor K. It would be V, just K here, V of T squared. Now, when you put the modulation, what happens is all the power, there's no negative part to power. So the power looks like this in time. If you talk about instantaneous power. Are you with me on this? Now, the actual peak power right here is going to be the square root of 2 times what we call the actual peak power right there. That's like when you did power. Do you all remember you took VRMS, IRMS to get power? Or you took what? V peak, I peak times 1/2, right? That 1/2 factor. Now that is the peak power right here. It's square root of, it's really, I'm sorry, it's going to be this value of peak power right there, and it's going to be divided by 2. Does that make sense to everybody, class? Now that would be, this is the actual peak power for an instant, but what we call peak power is the power in the on time. It's going to be the average power on the on time. Now the average power, so let me just do this. This would be the peak power right here. Right. This is the peak that we talk about times 2, right? That's the very tops of these things, but we never talk about this. We talk about the average power in the actual on time is the peak power. Now, when you look at this period, and then you talk about tau being this width, then when we talk about average power, we really take this time divided by this times this, and we get something down here, and that's what we call the average power. And it's constant throughout the coherent processing interval. Typically that's used, now the reason peak power will be used, and you're going to see this, a lot of radars have a very, very short on time. What they do is this. They have something where they have a very small burst, maybe 1/20th, maybe 1/50th of the actual pulse. The reason for this is they want very good range resolution. Remember, this value tau, right? Tau times the actual delta R is equal to, the range resolution is equal to tau times C over 2. So the smaller tau is, the better the range resolution. And they will do this. Target acquisition radars, by the way, are things that they don't probably even get into the details of any commercially marketed target acquisition radar that's used by the U.S. military. They'll never get into the specifics, right? But the idea is this: you want a very short on time with a very high peak power. Your average power is low, all right, relatively speaking. But the thing is, then it can differentiate 2 sea-skimming missiles very easily at different distances. That's the idea. And they also want super narrow bandwidths. So that's some of the thought process and things to consider when you're dealing with radar. This can be, it's usually, for the general radar range equation, this is termed, the beginnings of this is going to be the peak power in there, or really average power across that on time. You follow me? Now, you can adapt this and use average power, and that's what they do with search radars. Anyway, this is the power received, and I think everybody's got that part. Are you with me on this one? I don't know if people made stupid mistakes on this part of the equation or not. I always tell people to go through it from, when you're starting out, always start out with a target of sigma. You're transmitting a power, total power, PT. It hits here, comes back, the ranges are, and go through it step by step. What's the power that's painting the target? It's PT over 4 pi r squared times the gain of the transmitter, right? How much power is scattered back? You multiply that by sigma. Now you know how much is scattered back, right? And all that scattered power falls off as 1 over 4 pi r squared. Now you have the power density back here, correct? Then to catch the power and know how much you receive, you have to multiply it by the aperture, or lambda squared over 4 pi times the gain of the receiver. All right, go through that in your mind over and over again, and that way this will pop out all the time. You'll know it's proportional to sigma, it's proportional lambda squared, gain transmitter, gain receiver, proportional to power transmitted. You know that intuitively, right? The bigger the radar cross-section is, the more power you receive. It's inversely proportional to r to the fourth. And this 4 pi cubed is just a constant that chumps in there. Now, then you divide by the actual noise power. So the noise power will always be Boltzmann's constant times T0, and that's in degrees Kelvin. I'm putting a 0 on top there to make sure you realize it's not the period. Then it's times the bandwidth. And bandwidth is again something that usually is limited by the amplifier. It's limited by the actual electronics you're using. And yeah.
Yeah, I forgot what bandwidth was on the quiz. What?
You mean the value?
It was just 1 over tau.
It is.
It was written on the quiz.
Oh, it was?
Yeah.
I try to put some of the information down, put K down
See it.
too. But really, guys, this is the first up at bat. If somebody made mistakes on this one, don't worry. I dropped the lowest quiz anyway. I usually get all sorts of bizarre behavior in the first couple of quizzes. I have people that have unbelievable problems, like they forgot to get up and they miss it completely. All right, then this noise figure usually comes before that. That's a fudge factor. It has to do with the electronics and all the system, all the effects of the systems. And it really is a fudge factor. The way they calculate this, from my understanding, is probably the same thing you would figure out. You build the system, then you literally find out what the noise power is in the system in a very base way, and you adjust this noise figure so that it actually is, in fact, the noise power that you're seeing. Because K is something you're not going to change. The operating temperature you're assuming is going to be 290 or whatever it is, but it's usually 290, and it may fluctuate. The bandwidth is something that's pretty, it's nailed down based on your electronics, what you're doing. Now, you also have to take systems losses here, and then one other thing now, we multiply by the number of pulses. And that's the general form of the signal-to-noise ratio that you want to always go to. If there's anything specified about a radar, and you're wondering should I use search form, should I use track form? Well, the default, in track form, if they give you specifics about the actual, I'm trying to even think of the name of this thing, for a target, the standard deviation of the tracking noise. If they give you that, then you're going to have to use the formal form of the tracking equation. Right? But even with tracking radars, this is usually what they'll use to figure out signal to noise for tracking radars. Right here. Now that's where they start. Last time when we went down, we developed one. That's the general radar range equation. And we came down, we said we have there's two basic forms of that you can be developed from that. And the first was the search that I messed up. Getting to the final form, I went through it again in my office, but when we talk about the search form of the radar equation, let me just say one other thing. There are variations on this, but the fundamental form of the search form of the radar equation will always take the same signal-to-noise ratio, right? And it'll be for a certain number of pulses. And it'll come down to be, the way he has it, is going to be P-av. Now that's the average power over a period, T. And it's times the effective aperture. Now, it's assuming the aperture of the transmitter is the aperture of the receiver. So you have to realize this is for monostatic radars. This is important, because for bistatic, it's different. However, I've never heard of a search radar being a bistatic radar. That's target acquisitions are bistatic. We lock on the targets and track it. That's the one you want. Search radars, as far as I know, almost all of them, general form is going to be for monostatic, and it's this one.
Why the difference between search?
To be frank about it, all right, because when you are first bistatic are expensive. Just remember that. So when they take a search radar and they pan an area for something, all right, they can't see any stealth fighters or anything like that, usually. Now, satellites allow you to see something called a plume, or the thermal signature. From that, they can actually get the geophysical data of the location and go down there, and then the actual target acquisition radar can go and look in about that space and then lock onto it, but in the bistatic mode. And I'll be honest with you, I don't know if the weather radars, if anybody uses bistatic, I've just never heard of one. Most weather radars, even the ones that I'm familiar with, if you look at NOAA on their website, you can see, and they'll show the location of all the radars, and they'll show the actual radar profile, and they're all just, they're just standard search radars that are revolving. They're mechanically revolving, they're not electronically scanned.
They recently upgraded, or they were in the process of upgrading to a phased array right now,
Where though? Everywhere?
everywhere. Lincoln Labs built them a cheap phased array that they're now.
But is it a rotating phase array or stationary? I bet you it's
I
rotating.
imagine it's rotating, but it's also.
Yeah, and what that does, what I'm getting at, is there'll be a mechanical scan frequency. So it's not like you're gonna get a picture that just, you know, there's no track involved. They'll always have that. They'll present you the stuff. But every radar that I know that's used for weather radar and search is monostatic, and it's almost always, not always, but most of the time, with the exception of the Aegis class cruisers, it's a revolving radar. I mean, they have basically a turret, and the thing just revolves around at a slow mechanical speed.
You don't need anything better than that, right? Because weather's not like gonna
No.
suddenly like move.
No, but
you know.
he's brought up the thing with bistatic, all right? If these particles are trying to hide, then a bistatic might be of interest to us. But, you know, you gotta understand with a bistatic radar, when you have a receiver and a transmitter, right? Here, and you got a bistatic radar, well, just think about that. I mean, I don't know how many, you can have several receiving stations, but to do it for a search over 360 degrees, you have to have, I don't know how many stations you'd have to have. It would be a fair amount. You want to, like, you want a station out there collecting information for every 2 or 3 beam widths. All right, just think of the number that you'd have out there. You know, if they're 2 degrees, right? There's 360 degrees. So say we go 4 degrees. That's still 180 stations out there. That's an enormous amount. They only do this usually over fields of view, like with the military, as far as I know. They'll have a main illuminating radar. This is for target acquisition. And then they might have 10 different receiving stations that are all synced to this, so they know the signal being sent based on satellite time and things like that. They'll know the exact position of the sending signal, and they can get, when they receive their signal, they can triangulate and figure where the target is and the relative size of the target. But it's expensive as heck, and to have just 10 receiving stations is phenomenally expensive. And it's also hard to synchronize all this stuff. So what I'm trying to tell you is, as far as I know, search radars don't have that. But now, if you find one, you let me know, okay? Bistatic search radar. Are you looking it up now, Alec?
No.
Oh, well, I mean, if you find one, let me know. Anyway, so it has this. It's going to be, this is for search. And the important thing, it's power, it's average power times aperture product. This is real important because you're going to see with target acquisition radars, it's going to be average power times really the aperture squared or gain squared. It'll be proportional to the gain squared, and this is an important distinction. Now for search radars, we have that. Then we have the term sigma over r to the 4th. Those are just things you can't change. You'll have all the standard 4 pi. You'll have the 4 pi, k being Boltzmann's constant, T0 here, the noise figure, then you're going to have the losses here. And then they do us one better. They go ahead and put the actual frame search time in here divided by omega. And that, the frame search time by omega is a standard thing, and here's why. Because I can adjust, for a given known omega, all right, that's going to be the size of the area that's scanned, I can adjust this and slow it down or speed it up, right? One of the two, to get the actual signal noise ratio I want. And in his, the other thing that you notice about this, NP is associated with the dwell time. Give me 1 second, I'll get to you. NP is associated with the dwell. I'm going to put this down. The dwell time is assumed to be NP right here times the actual pulse repetition interval. This is important. Or it's NP divided by the pulse repetition frequency. It's not, they're not assuming an antenna dwell here where you would have more than one coherent processing interval per pixel. You with me, guys? Now, what's your question?
Did you forget the bandwidth at the bottom of that?
I did.
No, it's not.
Wait a second.
Or is it not in there?
No, it's not in there because the bandwidth becomes 1 over tau, and when we put in for the peak power, it's Average power times capital T over small tau, and the taus cancel. All right, and that's the other point. You'll notice even though this signal has NP in there, NP doesn't appear here, but where it's integrated is into the frame search time. All right, because for each pixel there has to be one dwell, all right, one coherent processing interval, and that's the key to this. That's the search form of the radar equation. Y'all seen that, right? Right, and you can, they modify this. This is gonna say, well, if we're designing a radar, what are things we can't change? We'll put them on one side. I can't change sigma, the target, the minimal target size. I can't change the range I wanna work at, the minimal. I want a radar adjusted for out to, say, 30 kilometers. That stays fixed, so this term's fixed. All right, now, what can I adjust? Usually this stuff I can adjust. Maybe I can adjust F a little. I really never have tried to mess with this stuff. But what am I actually designing for? It's average power times aperture and the actual frame search time. Those are the things I'm working with as things I can control. Go ahead. Oh. And when we do problems, you'll see how this bears out. Now again, that's the search form of the radar equation. The key thing to take from this is it is related to average power times aperture. Now there's several forms of the tracking, and this is, I call it target acquisition radar. It's a tracking radar. Tracking radars we talk about tracking radar. These always have narrow beam widths, very narrow. By that I mean theta 3 dB and phi 3 dB, less than 2 degrees typically, less than 1 degree in a lot of times. That's a very sharp beam, so it's like taking almost a laser pointer and shining it on the back wall and moving it across. And when anything changes the actual reflectivity of that laser pointer, then you assume it's a target. Think of it that way, all right? Very narrow beam widths on these things. I suppose there are some that are greater than 2 degrees, but they're very small. Yeah.
Yeah, I mean, that would still be huge at 50 kilometers or something, right?
Yeah, but remember, you're over 4 pi. You're over a 4 pi steradians, right? So that's still going to be what? 2 degrees by 2 degrees, which is what? In terms of steradians, there's 4 pi in a sphere, right? So that's going to be 2 over 180 times pi squared, right? 2 over 180 is really pi over 90 squared. It's very small in terms of steradians compared to 4 pi.
Okay.
And matter of fact, I used to know this. I forgot how many square degrees there are. So there would be 360 by 180, whatever that number is, square degrees in a surface of a sphere. And you could figure out if that's 2 by 2, that would be 4 square degrees. And take a look at that divided by 180 times 360, and that gives you the percentage of the actual spherical surface that's illuminated. Very, very small. It's like a laser point, basically. All right, now for these tracking radars, I was going to go into some more of the development of the search radar, but I think we're going to leave it there. For track forms, it assumes a bunch of stuff. In the book, he starts showing you the typical assumptions. First thing with tracking radars, at least for the legacy radars from World War II, they assume they have an effective diameter. A lot of times they do this for tracking radars. And a lot of this stuff, remember, was developed during World War II, really from 1928 to 1950, in that range. So they're going to assume, y'all see these kind of radars that basically are, they have a long, they basically have a long dimension here, D max, and then they have a small dimension here, D min. And the reason is this. All right, the longer the dimension, the narrower the beam width in that plane. So here it's long this way. You know what I'm talking about. You see these curved dishes that are rotating. All right, the beam width in the horizontal direction is going to be very narrow. The longer this is, the narrower the beam width in that plane. Does that make sense? The shorter, the wider. So they have a broad beam here and a very narrow beam here. And it's important because most of these radars, all right, target acquisition radars, when they go, this is just, the modern target acquisition radars are actually panel arrays. They're arrays that are electronically scanned for target acquisition. But in the old days, target acquisition, they had something like this to start with. And the beam widths were different. The beam width in the vertical versus the horizontal, or the azimuth versus elevation, were different. For starters, they say beam width, regardless of dimension, is in the book, and I'm just gonna go through this fairly quickly. This is beam width in degrees, and regardless of the diameter this way or this way for a parabolic dish, it's 70 times lambda over d, and this is in degrees. Now I'm going to mention d is diameter, it's not directivity. Now if you want this, you want it in radians, I believe it's 1.22 lambda over d, and this would be radians. That's what I'm familiar with, and that works. Now remember what you can do with this. Once you have beam width and they're narrow beam antennas, you can get effectively the gain or directivity. You always assume these things are very efficient, and you never distinguish directivity from gain unless there's a really good reason to, like there's a poor connection. So generally the gain is equal to 4 pi divided by what we call the beam solid angle, if you remember that before. That was the integral of the normalized power density over the surface of a sphere, right? But we just say this is approximately equal to, in radians squared, 4 pi divided by the beam width, 3 dB beam width of the vertical or elevation, and the 3 dB beam width of the actual azimuthal beam. And that's about what you get for the gain. When you go ahead and do the math on this one, that's gain. Let me do one other thing. We know that aperture, and that's what we like for search radars, and we do this for track too. Aperture is actually equal to lambda squared over 4 pi times the gain, so it becomes lambda squared, and I'll get out of your way, 4 pi. And then the gains are replaced by 4 pi over the 3 dB beam width, which means it's simply lambda squared over the 3 dB beam width. And that's the effective aperture. Now, when I go ahead and I put in this equation for beam width, and I can change this and I can say a D major axis, D minor axis, the major being the long one, the minor being this for the diameter of the dish. Then I get that the effective aperture, this is in the book. We can do it if you want. We can plug that in and we get lambda squared over 1.22 lambda over D max, and then 1.22 lambda over D min. You can go ahead and take a look at that. I'm just taking the information I put here, the approximate beam width. And these, by the way, these beam widths are for high gain antennas. So high gain is like over 20 dB at least, usually over 30. They're not for like half-width dipoles or something like that. And they're also for aperture antennas. And when you do this, you end up, you see that the lambda squared is going to cancel here, and you're going to get a value. He likes to break it out as 0.6 pi. He wants to leave pi out there over 4. I'm not sure why he didn't just make one single constant here, but he didn't, and it's times D max. Now he calls it D major and D min. It's really the dish diameters, the long ways and the short way. And if it's a circular antenna, it's just D squared, right? So that's it. And again, that's for aperture. Next, okay, now this is reverse engineering this. If I take this and want to see what the beam width was, and this is kind of neat. If you want to know the beam width and you have the aperture, then the beam width, 3 dB beam width, I'll put beam width here, would be equal to pi lambda squared over 4 times the aperture. This is just reverse engineering. First, We started with the beam width, we got gain, then we got aperture. Well, what if you have aperture and you want beam width? That's how you do it. With me? It's just reverse engineering. It's reversing the process. What's given? It's just another way of stating it. Now this is where the book throws out something. I gotta ask everybody this. How many have had a chance to read chapter 2? All right. If you've read chapter 2, you notice they throw out things and say this will be covered in chapter 9, chapter 14, right? Well, a lot of this will be covered later. They're throwing it all out here for one reason. You have to be familiar with the terminology to really go to the next step. Even though you don't understand it that well, you don't have to. I'm telling you, this is just the nature of this stuff. Because it's using, everything comes together with the radar. You got signal processing, you can have probability, you got electromagnetics, and then you have all sorts of method of assessing performance. Really, how do you label the losses? And that's another big issue on a system, is effectively finding a way to get a figure of merit for the losses. So that's the search form. The track form does one thing. It comes down here and it says that now we have something. Alec, are you looking on the page in the book where all this stuff is?
No.
Okay.
I am.
All right, what page is it?
For what?
For the track radar. Next, it's going to be noise. It's going to be the actual standard deviation of the tracking noise. And I'm going to put this up here, write it down. Standard deviation of tracking noise. I'm going to mention a few things about this. I'll put it down what it is. He says it's equal to the actual theta, the beam width in whatever plane, divided by Km times the square root of 2 times the signal to noise ratio. All right, so this is a standard deviation of the tracking noise. Now, he didn't define tracking noise, which begs the question, what is it? And here's what happens. When you track a target, noise is inherent. It's not just the noise that you're associated with thermal noise, a KT times bandwidth times figure, or noise figure. It's not just that. It's many other factors that we cover once we go through the signal processing, and we go through the actual error associated with quantization, and all that stuff. We start talking about how they actually come up with this figure. Hopefully we'll get to it. But for now, the only thing you know is, this is a standard deviation just like any other standard deviation. And what that implies too, and he doesn't show it here, is that there's a standard deviation of tracking noise, right? Then there has to be something.
Dr. McGinnis, what are the subscript on that sigma?
It's just theta.
Oh, theta.
Isn't that what it is in the book? Theta?
And is that Km?
Km, and I'm going to explain. Km is a fudge factor too. It's the target system parameter. Another ways of saying it's a fudge factor.
So it's K sub m.
Yeah. And I'm going to tell you, I would not in any way, shape, or form expect you to calculate that. If you need to use it, I'd state it. This is for a given system. However, this equation did come from somewhere, and the word standard deviation always makes you think of something. It makes you think of something statistical. Now here's the thing. We're going to get into this. If you have a target plus interference or noise, usually they put it this way. They say there's going to be some probability of the signal, and I'm going to get into all this in a second, if noise and signal are present. So it's signal plus interference. They use I for interference. It means noise, right, instead of N. And there's going to be a probability of a target voltage having a certain value. Now just bear with me on this one. And it's going to be equal to some constant, I'll just call K. It's a blanket statement because it depends if it's going to be the form of the noise. It can be a skewed Gaussian, it can be all sorts of different things. Generally speaking, it has the form of this. It's going to have an exponential minus V squared over 2 sigma, and this is the tracking noise right here, squared. Y'all remember seeing this? Typically, you saw this form. Now, what you actually saw, if you have only positive values for voltage, so it's rectified, you would get a voltage V V is voltage in this one. And then you would be divided by sigma naught squared. And here, V has to be greater than or equal to 0, so it's rectified. Do you all remember that distribution, guys? All right, actually, I didn't do it right. It's V minus V actual target signal, call it that, right there, and squared. Now let me explain this. This is called a Rayleigh profile. Do y'all remember the word Rayleigh from your Did y'all have, you had Stan Reeves for random signals and systems? Do you remember that there was the first curve you saw was something called a Gaussian curve that went from minus infinity to positive infinity? Well, the integral of the probability density for any probability density function from minus infinity to infinity is 1. The event has to be there, in other words. It cannot be there, or else this whole thing falls apart. Well, when we talk about the probability density function for a voltage with noise, do you follow me on this? And I should say this should be Vs here. Then what they say is if you look at this, and I'll try to draw this, what I'm trying to do is give you some context to this, trying to show you where it's used, all right? So, and we're going to get to this today, but I'm just trying to do it. So right here is where the actual voltage is from the target. Remember, signal goes out, hits target, comes back. Ultimately, it produces something called a voltage related to the size of the target. Are you all with me on that? Now, if we looked at the probability density function for the actual voltage Vs with noise, then you get something like this. All right? The entire probability, if you integrate it from 0 to infinity of this thing, would be 1. But you'll notice the target is here. I'm saying that should be the voltage if there were no noise. But when we measure it statistically, what we see is this, and this is where it gets a little bizarre. If this is time, remember, there's no time in here. This is based on statistics. What you're going to see is something like this. You're going to see a threshold here, V threshold. Anything above that's going to assume the target. And then you're going to see this. All right? Now, statistically, what we're showing is the value, if there's a target and noise, that's the statistics of the value of this function, the voltage. So if you look in here, if your voltage is from here to here, right, chances are it's a target. I can go a step further. I can say, don't even put an upper bound on that. This is going to be 1 standard deviation. If it goes from some V threshold all the way up to infinity, there's a target. Does that make sense? Because the bigger the voltage, the more likely the target. If there's something out there, there has to be, right? So that's where this comes from. And this is the tracking noise error. And the way we determine it is later, where we get into models called swirling models of targets. And what I'm putting this all here because it's mentioned in chapter 3, but not explained. So here's what a swirling target model does. I want you to just think about this. Suppose you're a radar and this thing's coming at you and it's solid metal and it's tumbling. What kind of radar cross-section do you see? Think about it. Well, it looks small there and big there, small there, big there. It's something that's time varying, right? It's time varying at the mechanical rotational speed of this object. Does that make sense to you? All right. Now, statistically speaking, we can categorize that very easily in terms of the probability density function for the voltage associated with the size of the target at a given range. Just go with me on this one. We can, in other words, we can more or less get the details. So once we measure this with a radar and we look at a time script, we can kind of get the statistics and we can locate the likely target. So it has to do with target classification. There's also a probability of not seeing the target when it's there, and the probability that no target's there, but you're seeing a pseudo-target. You think you're seeing a target. So these are all the things you consider. Got it? I'm throwing a whole 9 yards, trying to make sure you understand the scope of what we're up to. Okay. Now back to this thing. Well, that equation right there is very poorly explained. All of it comes later. You're just going to have to accept it on faith. All right? It's like the speed of light is a constant. First time you're told that, and any reference frames thinking, why? Well, who knows, but that's just the facts. You got to take it on faith. So now, when you go ahead and incorporate that over there, the sigma 3, or theta 3d the beam width is pi lambda squared over 4 times the aperture to get the beam width. Into this equation, here's what falls out. Anybody read this part? Do you remember reading it? Or not?
I thought that was in chapter 1 that I read it. but-
It's not chapter 1.
This is chapter 2.
It's like the, yeah.
This,
Okay, yeah.
but the thing about it is, there's so much that's, where did we get it? It's, he's coming out and mentioning chapters 14, 9, stuff like this. What I'm trying to do is give you perspective on why that's important, where it comes from. We'll get to how it's measured in a bit, how it's actually determined for any target. So now, we find when we take this, if we solve for signal to noise ratio, just go with me on this one. Well, you can see what happens. If I want signal to noise ratio, and you don't need to write this down, just work with me. First, I'm gonna multiply by Km over here. Then I'm gonna divide by the beam width. Right? Now I've got that. Then I'm gonna take this thing and square it. Now I've got this. Then I'm gonna multiply by 2. Now I have this, and then I'm gonna invert it. So I get signal to noise ratio is equal to 1/2, and then Km sigma, tracking noise error, over the 3 dB beam width squared. In his book, what he does, he's gonna take that beam width equation, do you see that one over there, pi lambda squared over 4 pi, stick it in here, and when you do, you get his form, which is pi lambda squared over 8 effective area, aperture, Km squared, and sigma, this is the tracking noise area squared. I don't expect people to memorize this equation. I want you to tell you, because there's so many variations in this one, I will give you this information. The one you have to memorize is the fundamental one that I call the radar range equation. That one you have to have down, all right? I'll give you the search form, and I'll give you the track form, got it? Because I know you can foul these up sideways, all right? And there's a lot of variation on that. But the fundamental form, I want you to know. So now this is the signal to noise ratio for a tracking radar. And it looks quite different, if you look at it. For instance, there's no gain, there's no power, right? There's all these other parameters. Now, built into this, the gain appears there, obviously, because if you have aperture, you have gain. But here's the thing, all these other parameters deal with frequency, power, and all that other stuff in their ratios. So that's one form that I don't like. Matter of fact, I don't use this form. I never have, I never will. Something else that I have to mention, and I'll show you this in a problem. With tracking radars, they have to be on the target when they're tracking multiple targets. There's something called the actual rate that they have to be on the target. So if you have 6 targets, every second they have to illuminate with at least 1 dwell time those targets, maybe 5 times. 6 targets, right? You have to illuminate each one with at least 5 dwells, right? So that means 6 times 5 is total number of targets, right? 6 targets times the dwell time. That's just for 1 illumination per second, right? There's an update rate, so per second, if you had 5 targets, it would be 6 times 5 times the dwell time was how much time per second would be spent illuminating those targets. Does that make sense to you? I'm gonna go to a problem in a second. Now, if that's the case, right? If you're in both search and track mode, which radars operate in, they're searching a space, but every second, they don't search the whole time. Part of that is gonna be parsed track. So if you have 1 second, but you're using 520 millisecond, or say 480, this is a problem in the book, 480 milliseconds have to be dedicated to going back and tracking. Make sure the targets are there. If they move, you've got to reposition and locate, right? Now you have 1,000 minus 480, or 520 milliseconds left to search. Does that make sense? And this becomes important, which means about right now I'm going to do the problem where this becomes clear, because with track radars, you have to have an update rate on the track. And it's usually 10 times a second you have to illuminate that same target to make sure it's there with 1 dwell, at least.
Does it depend on the velocity of the target?
Probably. And to be frank about it, it would make sense that a hypersonic thing has to have a lot more tracks per second than something that's a blimp. It just makes sense. But in any case, there's a certain update rate. Now, I'll tell you one other thing about this. Modern radars, you can't do this with mechanical scanning, right? That it's forbidden. You have to have an electronically scanned. If you're going and jumping at 6 or 7 different positions per second with multiple dwells, it's the only way to do it, and it has to be an electronically scanned array. The second thing is this: what will become very, very apparent shortly is that the power needed for track and search combined becomes excessive. It becomes something where it becomes a very costly endeavor. And that's why track and search is always almost military, with the exception of air traffic controllers. And I consider that because human life's involved, they will spend the money on that. But Atlanta radars, the one I was told about, now I don't know if they got, you tell me they got new radars for the, I wasn't even aware of this this, and the National Weather Service is going to install all these phased arrays, right? That
Yeah, I
MIT
think they're
developed.
electronically steerable as well.
Have they installed any?
Yes,
Where?
New Mexico.
You mean New Mexico or Mexico?
New Mexico.
Okay, but nothing in the U.S.
New Mexico is in the U.S.
I mean, sorry. New Mexico, nothing in the state of Alabama or any other states?
Correct.
All right. New Mexico is a
Sounds like a Sandia National Laboratories experiment.
Oh, Lincoln Labs designed a prototype and they installed it and it's been working for the past couple of years.
Is that at Sandia?
I don't know.
But the national labs all work together. The fact is this, that what I'm talking about with search and track at the same time, it gets ungodly expensive for a lot of this stuff because of the power. And you guys, are you involved? Do you like high fidelity sound, stereo stuff? I mean, or what is it, surround sound stuff? Well, 100 watts RMS has a price tag if it's got fidelity, right? How much is 1,000 watts RMS system? Does it go up linearly?
Squared.
Probably goes up by to the 1.3, 1.5 power. I don't know if it's quite squared yet. For every watt that you want to transmit, the price doesn't go up proportionally, or the cost of doing it. It goes up about squared, I think, maybe to the 2.5 power for power amplifiers at high frequencies. So what I'm trying to tell you is, when I say it's costly, it's not just the electronics that do the data processing. To get power amplifiers that can do this with fidelity gets to be very expensive. And here's another problem, and this is the reason all digital radar is so interesting. Whenever you have a radar and you have mixers, these are stages where you have intermediate frequencies and you're going through it and you have power amplifiers, then power dissipation becomes ridiculous for things that are airborne. And you have to bring in liquid cooling, and I don't even know what they use on some of the jets. I know the front ends of 14s had all sorts of clever ways to get rid of heat. Now, you know, you've had your laboratories and stuff. Did they show you how to put, they call them thermal sinks. You just clip them on, they're chunks of metal, you put them. How did it come down here? Scam likely. I thought that phone didn't work.
You should have just answered him and let him listen to your radar lecture.
So I just looked it up, and apparently the Lincoln Labs radar is a FAA and NOAA are using the same phased array for both of their purposes.
All right, so that means navigational radars, or I should say tracking navigational radars here for Atlanta are also using, maybe they do have.
No, the same radar. So the FAA and the NOAA have pooled their money together,
okay.
and they bought these phased arrays, and they're both using it of the data.
Are they strictly search or search and track?
Since they have one in Oklahoma too.
All right, because search and track are, I mean, Atlanta Airport has track radars. They have to.
Yeah.
But search track radars are super expensive, and I don't know if that's a search track or just search. It's a weather radar though, right?
It's weather and aircraft.
So it is track.
It does everything all at the same time.
And how much is the price then?
It says the
Low cost.
For the government.
Yeah, right.
They're like 600
Well, no,
toilet
it's
seats.
not particularly well funded, so. it's
Yeah,
probably
this one, it
actually
says
low
the
cost.
Navy actually gave them $10 million.
Yeah, so that's like 2004 is, I just read that page, and then this Lincoln stuff is from like 2015, but I can't find any good articles on it.
Anytime if it's a military application, they don't have a ceiling on the budget. Trust me, if they need it, they got it. It doesn't matter. Now, if it's just some study, I don't know, hermit crabs in Alaska or something like that, then if they get $100,000 to do that, we think kind of radar would be really a miracle.
This just said it was decommissioned in 2016.
I think it was decommissioned in favor of this new one.
It's probably a new phase of the project.
Yeah.
Okay, so that's one form. Then the form that you're going to see and use a lot is this form. Now, remember, I'll give you that, and the thing is, this thing's very odd. You don't see transmitted power in here. You don't see a lot of things that you would assume should be there. You do see aperture. Just remember that. One other thing about this particular form, you see how it's inversely proportional to aperture, which makes no sense? Y'all see that? The fact of the matter is, it's because all this stuff's buried in here that we don't see. All right, it's buried within it. We could prove this if we had a little more time. So now I'm going to show you the form of the target acquisition radar that is probably mostly used for the problems and in the real world. And this is the one you're going to have to, you'll be using. Okay. Matter of fact, before I do that, let me go to the problems 8 and 9 in your book. And I want to do these because they'll really showcase the importance of update.
I got a question for you for a second.
Go ahead.
So is that a use again next to the?
What's that?
Is 1/2 what?
It's KM, sigma, this is the tracking noise there, over the 3dB beam width squared. And then what I do is I replace the 3D beam width with that equation over there that I had. All right, and I just stick in the aperture. Then it becomes 8 aperture KM squared, tracking noise squared, and then on top it's pi lambda squared. Now, a lot of this doesn't mean anything to you until you see it in problems. And this particular form is, you're oblivious to how you even came up with that thing. But the next one's a little more apparent. Before we do that, would you read, and I want to do this. Yeah, time. I got probability to do. I got in phase and quadrature, noise. Go to 3.9 first. Alec, can you give me 3.9 or?
The problem or the?
Yeah.
3.9?
3.9 the problem. This is, and then we're going to do 3.10 too. Then we'll get to the probability.
Consider a weapon locating radar having a beam width of 2 degrees in both azimuth and elevation that is set up to surge a volume defined by a 75-degree sector in azimuth and a 4-degree sector in elevation.
It's 2 degrees, right?
Yeah.
All right. Always sketch out the region. So in azimuth, or in the horizontal direction, you've got 75 degrees, correct?
Correct.
And then
4 degrees.
4 degrees. All right, now, what else did you say? The dwell time was what?
2.4 milliseconds.
Make sure you can do this one, so I'm gonna slow it way down. All right, dwell time is the important part.
And 5 dwells at each location.
So the 2.4 millisecond, and they want 5 dwells, right? Per pixel. Now here's what you do at that point. Figure, this is like an antenna dwell time. It's the number of coherent processing intervals, right, times the actual time in the dwell. So what you do is simply find out this. You can call it T antenna dwell. This is the time you're going to spend per pixel. So it's going to be 2.4 times 10 to the minus third times 5. That's the time you have to spend per pixel, right? We're going to get the frame search time next. All right, everybody with me on this one? It's straightforward if you think about it. A dwell's 2.4. You have to spend 5 dwells on each pixel is what he's saying. All right, now how many pixels do we have? And here's where a mistake is made. I'll stop for a second. See, I had coffee this morning. When I don't have a cup of coffee, things go off the rails. I found that out. You ever walk out of the house without your wallet or your phone? And if my head wasn't attached, it would have been back there too a few times. I see Marcus. You ready? All right, now we figured out how many pixels. Here's a common mistake. People will say, well, the total number, they'll say the space right here is just going to be 4 times 75, all right? And they just divide that by the beam width squared, which is 2 squared. And they say, well, that will be the number of pixels. That's wrong. This would be m, the number of pixels. We know that we're going to have pixels, right? We're going to have a whole bunch. But here's the problem, and you got to remember, they did this on purpose to try to get you a little nervous about assuming things. 75 here, the beam width is 2 degrees. So how many spots do we have?
76, or
Ah, you're right, we actually have what? No, I mean, we would have, well, if you think about this, 75 divided by 2 in the horizontal direction, how many slots? If you divide that by 2, right? 76 by 2 would be 37.5, you can't have a 0.5. So you always round up, all right? So the number of pixels we have in this direction would not be 75 by 2, it would be 75 by 2 plus 1, or it would be 36. 36 pixels, or 36 spots or spaces. Now in the vertical direction, we're gonna have 2 spaces. There's gonna be just 2 columns, right? 2
So
spaces.
you could, is that the ceiling of 75 divided by 2? Is that what you said?
Well, what it amounts to is,
You round up.
you have to round up. This is gonna be, what, 35.5, and you've gotta round up to 36, correct? Have to be, it has to be an integer
You
value.
round up to 38, it's 37 and a half.
Or 30, I mean 38, 37 and a half, you have to round up to 38. And I want to tell you this is a trick problem. He just was getting to the point when you're doing a search radar, you remember you got to search the entire space that's designated. And you can't like be negligent at the corners. As well as for track radars, you can't either. But and search is really bad.
So is that supposed to be a 38 instead of a
Yeah,
36?
it is. I'm sorry, Marcus, you're right. 38. So now we can say that that the number of spaces m would be equal to the number of pixels. This is going to be the number of spots, all the way out to m spots, that we're going to have would be 4 times, in this case, 38. And then we're going to divide that by the beam width, which is 2 degrees, so squared. So that means we have 38 spaces, right? 38 pixels, if you will.
Horizontal.
Huh?
Horizontally, you got 38.
And then you have to multiply that. Well, let me do it this way. This is
Wouldn't you
4
just-
degrees vertical here, so I multiplied, there's really just 2 spaces. Actually, let me do it this way. This is be the best. I know I have 38 in the horizontal direction. How many spaces vertical? The beam width's 2 degrees. 4 by 2 is 2, right? So it's times 2, and that means here, I'm going to have 76 pixels. Now he will use pixels and he'll say spot sizes, and he'll use different words. They mean the same thing. It just means how many different places do I have to locate the beam electronically when I'm scanning? That's all it means. Now, at each one of those spots, I have to spend this much time, right? So the total time it takes for a frame search, this would be the frames, how long does it take to go through the entire area one time? And that would be equal to simply m, the number of pixels, times the antenna dwell time, but I'll do it this way, times 1 dwell, times the number of dwells, which is 5. And then we'll put the numbers in, so it's 76 times the antenna dwell is 2.4 times 10 to the minus third, and then it's going to be times 5. And I want to say that's 480 milliseconds, but could somebody just punch those numbers, please?
It's like 960.
Or 960, pardon me, if you're right. 960, is that right? 960.
Ish.
What else did they ask on the problem?
I think that was it. Yeah, that's it.
And are you looking at the solutions? Or not? That's the solution, I know. I looked at this last night. This one. Now, the next problem is
So that's the total time to scan the entire thing?
one time. Go through that one time. That's the amount of time it takes, right? The next thing we're going to deal with is a tracking form of the radar equation. It's going to, when we track targets inside of a search radars, so basically we're going to do track search. Track always takes priority. And I've got a couple of questions here. I'm going to try to slow this down, make sure everybody understands what I'm getting at. So in the next problem, this is going to be 310. Go ahead, Alec.
For which one? 310?
310.
And also my name is not Alex.
Oh, sorry, Alex. Sorry,
If
Alex.
there are 8 targets being tracked by the system in problem 9, each consuming 6 milliseconds per track update at an interval of 10 hertz.
Hold
what
it.
is-
8 targets. I'm sorry, I'm not as fast as you. Go ahead.
6 milliseconds per track update.
So we have, all right, the delta T is 6 milliseconds?
Yeah,
6 milliseconds, and then the update rate is
10
10?
hertz.
Huh?
10.
10 hertz. All right, go ahead.
What is the new scan search time?
Okay. Now these parameters here have nothing to do with the search space at all. All right? You've got 8 targets. You have to spend 6 milliseconds on a target. You have to do that 10 times a second. You follow me on that? So how long does it take to do it 1 time a second? Well, 8 times 6 times 10 to the minus third, that would be how much time it would take to do all these targets once, right? But we want to do it 10 times, so we multiply it by 10. And I believe that's 480 milliseconds, right? Now that means per second, 480 milliseconds have to be spent tracking. Y'all see what I'm saying here, right? Per second, remember that. So what's the maximum number of targets you could track? I think you see what I'm doing here. If it was only 1 target, it would be 6 times 10 to the minus third times 10 for 1, right? 2 would be 2. 8 would be 8 times 6 times 10 to the minus third times 10. That's 480 milliseconds per second. You follow me? This is per second. It's a rate. It has. So what's the upper limit to the number of targets? Per second, how much can you use of a second? 1, right? Just 1. All of it, yeah. So that means over here you would place 1. Then you would place n. That would be the maximum number of targets. Do you follow me on this? I'll go through it slower. I know for each target I have to do this 10 times a second and spend 6 milliseconds. So it's really 60 times 10 to the minus third. So the maximum number of targets I can track, according to those parameters, would be n, would be 1 over 6 times 10 to the minus 2. And what is that? I don't know. It's what? Well, 10 to the minus 2, 1 over is 100. 100 by 6 is what? 50 by 3, huh?
Answer 16 and 2/3, so 16.
16 and 2/3 targets. Really, the most you could do would be 16 targets. That's when you're using all your update rate per second. The entire time you're doing nothing but tracking. Follow me? We're gonna get back to the actual problem. This is a real good thing to start. It kind of immerses you into what you have to think about when you're doing a search track radar. And I've never built a search track radar, but I've been involved with a lot of the stuff thing I'm doing now is using an encrypted key with a radar signal. We're trying to get paper finished with this, and I see all the parameters with track and search. And I'll get into a lot of the problems we ran into later, but it's very interesting, the upper limit on targets. By the way, how many targets do you think a military radar should track? By military, I mean land-based. I don't mean like an F-16 radar. Should be able to effectively. An AWAC.
50.
Hundreds. At least hundreds, all right? Hundreds. Because they have to run a battlefield. And you're going to have drones. I guarantee you I know what I'm talking about here. Drones, they have to track jets, our jets, their jets, they have to track, including Katyusha rockets and everything else. They have to have battlefield management. And so it's hundreds of targets they have to track with update rates that probably are higher than that. Just want to give you some perspective on that. That's real battlefield stuff. You know what an AWAC is? It's a plane with a big disc on it. That's the type, that's the numbers you're talking about. Airports probably have hundreds too, and I don't know that for a fact, but I'm just going to say when I flew in, if you fly in and out of Atlanta, just look around you how many planes are in the air. All right, there's a lot. When I was on the carrier Eisenhower, I remember going down and watching. We had a legacy radar. It was a 49 2D radar, and just looking at how many beeps there are out there. Now most aircrafts fly in formation, right? So you might get 6 pilots flying one way, another 6 pilots. Then you have aircraft not associated with any of the exercises we're doing. And I mean, there are a lot. Now this is just a navigational radar, so we're not tracking them. But believe me, if you're a guy managing an airfield or something like that, you probably want to know exactly where those targets are every single second, because it only takes one non-compliant vehicle to get in your search space to mess up everything. And I don't even know what the latest is on drones. There's been a lot of legislation they've tried to get across where drones can't fly above a certain altitude without licenses and stuff like this, and they got because in the Atlanta airspace, when these planes come in, they're not like 1.5 miles high and just go straight down. They come in at a glide path, and they're thousands of feet and even hundreds of feet at the end off. Well, a sizable drone's in their way. It's completely, so. You know what I'm talking about with drones, right? I don't mean the little ones you buy in a store that, or, these, what do you call those 4-prop toys. I'm talking about drones, commercial drones that you can actually, if you're the press, you can obtain and use for, photography work and stuff like this. And they're up there they're up there at least thousands of feet. I don't know about tens of thousands.
There's a new proposal out for drones to add the ABES, is it ABES? The
Automatic-
transponder that.
It's automatic, no, it's the
Yeah.
ABDS,
Yeah,
Automatic Detection Broadcast System.
yeah. Yeah, there's
It's
a
a long-
requirement that drones are gonna have to, above a certain size.
Big
or something,
drones.
have those.
Have you seen any large drones ever?
Yeah.
Huh?
Yeah.
Most of the time, they're in military areas, the ones that I'm familiar with, that I know. But now the press is buying them. People that want to take, or people that do wildlife management, things like this, where you want a view of a large area cheaply. And they're available now. I don't know if there's any jet ones available to anybody but the military, but they're out there. These prop ones are all over the place now, from what I can tell. So getting back to this thing, when we look at this, we see if we have 8 targets and we got 6 milliseconds per target at a rate of 10 updates per second, we get 480 milliseconds that have to be expended per second on tracking. Now go back to the next part, Alex. No, that's not it?
It asked the scan search time if that's happening while you're trying to search.
So now we're gonna have search integrated with tracking those. They want what the frame search time is. This is important. So what happens to this? Well, if you think we have 480 milliseconds per second used simply for tracking, that leaves 520 milliseconds for search, right? So that means you have 520 milliseconds for search. Now here's how that works, the next part. I saw I needed 960 milliseconds, right? For the actual frame search. How much is that gonna how much longer is, that's per second, by the way. it's 960 milliseconds, it would be per second if you had a track radar integrated with this. So how much longer is the frame search? Well now, remember this is actually 1,000 milliseconds, that's the amount a second, minus 480 milliseconds, that's the amount left. So now you would say, take the frame search time with no targets, this is with no targets, and divide it by 520 milliseconds. And this is 1.75, so how much longer would it be?
7.75 seconds.
I don't know, tell me.
Yeah, it is.
I just want to see, what do you get if you put 1.75 divided by 1.75 divided by 0.52? No, it ain't.
No, it's 0.96 divided by 0.52.
I'm sorry, that's
Which goes down to
0.96. The frame search time is 0.96, so it's really 960, right? By 520, and what does that come out to be? It's not 7.
It's 1.75.
What?
1.75.
Yeah. Is that what you said?
Yeah, that's what I said.
I thought you said
That's
7
what I-
for some reason. Anyway, so now instead of 960, it's 1.75 seconds, which means you don't do a frame search per second. Now the time it takes to search the space goes up and up. And in the limit, this goes to infinity when you're tracking as many targets as possible. So just make sure you understand. Do y'all see what I'm doing here? That's the update rate I wanted to talk about. Don't I have at least 5 minutes? You look like you're ready to pull. All right. Next, we're going to talk about, I can tell you this, when you read the part about clutter, all the stuff where they talk about a clutter field and stuff like this, they always come back with something that is an effective radar cross-section. All right, clutter is something you don't want, wish wasn't there, it's there. It can be volumetric, like volcanic ash or a rain field, Or it can be a solid piece of clutter like the seawater. And what happens is when you're using a radar, you have to figure out how much power is going to come back from clutter. And so they associate nothing more than a radar cross-section associated with clutter. It's called a clutter cross-section, but it's just a radar cross-section from the clutter. Does that make sense to everybody? There's volumetric clutter, and in the book you can read about. There's also going to be clutter associated with water and with trees. Yeah.
So how does volumetric clutter work? Because if the radar is going into a volume that's reflecting it uniformly,
It's an effective
all of
value.
it should come back.
Just think of a rain field. If you have a rain field that's a centimeter wide, straight down, long sheet, right? Radar's hitting it. Well, most of that is air, right? There's only a couple of drops, right? Now there's more raindrops the next one, right? So if you're looking at this from a radar and you hit it, what you get is something, well, the first set of drops scatter some, next set of drops back here scatter some are rescattered. Go ahead.
So what I mean is that like the integral of a sine wave is 0, right? So as it goes through the volumetric clutter, shouldn't it all come back completely like destructively interfering with itself?
It's the time, the length of time. The thing is, the actual, because it's a speed light, I know where you're going with it. You're thinking, shouldn't this be more of you're thinking it would be like noise, not adding itself in a way that'd be constructive, right? But the thing about this is with clutter in general and stuff like this, raindrops are spaced small, right? Small distances away. You are right, there is a portion of this that's destructive interference, but when you get the ensemble of raindrops, there's actually a program that we do this with. It's a ray tracing code, not a moment method code, but you can take raindrops, make them ellipses, there's a certain reflectivity each one has, a certain radar cross-section. You can put the ensemble out there, make it as thick as you want, send in a signal, it's in the time domain, they do modeling. You'll see as you increase the actual depth of that thing, it'll asymptotically hit the maximum reflectivity, right? The deeper you get. There is some constructive, some destructive, some of that's scattered off into nowhere, but a good chunk of it's scattered back at you. The amount scattered back is the clutter cross-section. And I have to be frank about it, it's probably not based on theoretical modeling as much as measurements. And I'm just saying that because whenever you get an ensemble of a large number of particles, they have to do what are called Monte Carlo simulations to get answers to the effect. I got about 2 minutes. So in the last 2 minutes, now I'm just going to talk about probability. I just said that about clutter because I don't spend much time on it because it's so obvious. It's just a radar cross-section. That's all it is. Now, we're going to talk about probability. And the reason we talk about probability is detecting a target is never an absolute certainty. There's a probability that the signal you have indicates a target, and there's a probability it doesn't. So when we start with statistics, the first thing we do is start with the probability function for a voltage V. Usually we start with something called a Gaussian distribution. So if this is voltage, the voltage can have both negative and positive values, and this is just V here. And this shows you the PDF of this voltage. Now, the probability that the voltage will be greater than some or equal to some VT, some threshold voltage, will be the integral from the threshold voltage to infinity of the PDF of the voltage dV. Typically, the actual PDF of the voltage for the first type is a Gaussian. This is going to assume the voltage can have negative and positive values. It never does in the real world. We rectify this. And you get this. It's going to be some constant, all right? And don't worry about the constant's value, times e to the minus v squared over 2 sigma squared. Here, sigma is the standard deviation. And I think you all remember that. That's general statistics, right? Now, when we talk about the probability density function for interference, then you put a sub I, that's noise. The probability density function for interference is something that always has a mean value of 0 if you don't rectify it. You all follow me on this? And it has to do with white noise. You know what wide sense stationary noise is from, you have that in random signals and systems, right? It means that noise itself is uncorrelated. Yeah, I know. Time to go. I'm going to finish this train of thought, though. All right. Now, the minute you take this voltage and you rectify it with some sort of an absolute value, follow me on this, just think of a full wave rectifier circuit, all right? Now these statistics do this. And they shift to something called the Rayleigh distribution that you're familiar with. The Rayleigh distribution is the one we're going to talk about. And I'll pick that up next time because Alex is chomping at the bit to get out of here.